All right. We're ready to turn to our partners. And Chris Root, are you out there and ready?
Yes, we're ready. Sun has come up in California, so my coffee is empty, so we're good to go. So I believe I have about 20 minutes.
Yes, you do. Do you have visibility on your DCO? Can you see the slides?
Yes, we do.
All right,
yes,
very good. All right, reminder to everyone. Everyone who is not speaking, mute your phones. Thank you.
Okay, so
please take it from here.
I'm Chris here in the. Thank you. This is Chris Root here in the light blue shirt, and sitting next to me is David Price. He's one of the co-authors of this paper. Robert Yogi Kessler, who's at Cherry Point. I believe he's on the line. We'll be speaking later, but he is also a contributor to the topics in this presentation. This is kind of highlighting the indirect parts that we can produce here at Fleet Readiness Center Southwest and across the NAVAIR depots. Next slide, please. Next slide. There you go. So the outline for today's talk is kind of talk about ConFRC, who are we, what our technology and insertion efforts are all about, how we've been utilizing advanced measurement reverse engineering. Connie alluded to it a minute ago, as that's a key part of some of the work that we need to do in order to produce these additive manufactured parts. And then really in the spaces today, we're able to do a lot of indirect parts, meaning not end-use items that go on the aircraft, but things to help us produce those end-use items in the areas of trim tools, sheet metal tooling, and rep and composite tooling. Next slide, please. For those of you who are not familiar with NAVAIR's Commander Fleet Readiness Center's locations and activities, this is kind of a real eye chart, but there's 6 Fleet Readiness Center locations. 3 are primarily depot level, and 3 are primarily intermediate level with depot level support. Most of the additive manufacturing efforts are happening at our depot level facilities. One out here in San Diego where we're located is FRC Southwest. We also have a facility in Jacksonville, Florida, that's southeast, and then FRC East in Cherry Point. What kind of makes this a useful and innovative group is that we're tied in with our NAVAIR acquisition and weapons systems engineering leads, and those are at Pax River and China Lake. You may have heard of those facilities. So as an enterprise, we're able to leverage across both domains, acquisition, certification, and as well as depot level repair and product support. So keep that in mind. We're a big organization, about 32,000 employees across the enterprise, and we're now getting into this additive manufacturing kind of a big way at our depot level facilities. Next slide, please. What kind of makes this real useful as well is we have a technology investment integrated program team that allows us to collaborate efficiently across these 6 FRCs and in the area of additive manufacturing, primarily the 3 depots, working closely with some of the folks at Pax River and China Lake. Several of us are on the rare parts team, as you heard Connie mention. I'll highlight that a little bit later. But what this allows us to do is talk amongst the enterprise about the needs and requirements. You see some of the activities there. It allows us to identify funding, collaborate on several projects related to additive manufacturing and other areas, but certainly since this is about additive manufacturing, I want to concentrate on that. An area that the team includes your aircraft engineers from our research engineering department. We tie in with our industrial engineers, which includes tooling and facilities, industrial equipment, but we're beginning to add information technology and information assurance, because as you know, moving digital data files across the enterprise has a high level of information technology requirements and needs, and we're adding our logistics IT and tech data leads into this team as well, so we can really collaborate on the new technologies that are going to be needed to not only support additive manufacturing, but model-based design, model-based definition, and basically a model-based environment. Next slide, please. Kind of ways we do this in the intersection of these overlapping circles, it's really seeking and identifying new technologies, enhancing our skills within the depots on how to use these things effectively. And by doing that, you certainly can increase and support new workload and enhance your capabilities there. A variety of means there, but the one I think that we're finding, as Connie alluded to, is the collaboration between industry, universities, and government organizations like OSD, Austin Naval Research, AFRL. We've got a lot of activity going in these areas, and that's where we can take the best minds and activities that have taken place and put together great programs. Something else that recently occurred was the depots, 2 of our depots became federal laboratories here at North Island and at Cherry Point. And so that allows us to do cooperative research development agreements with industry and or universities, and that's given us a little edge there on how we can evaluate new technologies and look at new ways of using these in a very cost-effective manner. So that's kind of the approach we take to insert new technologies. Next slide will go into details about the actual use. So next slide, please. This kind of started our journey. My role here has been Advanced Aircraft Technologies IPT lead. My background is in aircraft structures, so I was really involved in a lot of the aircraft repair work that was going on at the depot. Majority of our engineering support is in support of the aircraft structure and components. So what we found was really valuable was to have the ability to take measurement systems and measurement technologies and put this together in a laboratory environment to really accelerate our repair design. And this is before we had additive manufacturing. This is in the 2009 time frame. So you see there in one of the photographs, you see one of our, David Price, the gentleman sitting next to me when he was an intern, being trained under Gabe Dragisevich on how to use some of our new laser scanner equipment to go out and take measurements off of aircraft. We morphed that technology through software and were able to come up with some great ways to rapidly identify dimensional variation in aircraft parts, enhance our model-based design for tooling, and feed a whole host of products that are identified under our joint lab work. We also invested heavily in a lot of nice equipment, so we have probably the best set of measurement and rapid prototyping equipment available to NAVAIR at this point. And again, this is shared across our enterprise as needed. So this is prior to 3D and additive manufacturing, but we had the capability to create a lot of great models. We realized the next step, and the next slide goes into it, was the ability to go into rapid prototyping. So this is our initial journey, and it was primarily for tooling. And if you look on the slide there, you'll see in the top photograph or image, that is a form block for a sheet metal tool. And we were working these out of the old hand whittled method, as I call it, to a shape, and a lot of iterations to get to the shape you wanted. We were able to go in and scan these tools, which wear out over time, and produce them out of additive manufactured FDM, and put those through a series of tests to see how long they would hold up, and never really damaged the tool at all, and never yielded it, and certainly it served the purpose. So we found it to be our initial use case for additive manufactured parts was for sheet metal tooling. As you can imagine, on these old aircraft, there's a lot of sheet metal parts, and so this was pushed, and a lot of this work was done under collaboration with the Rare Parts team, because we didn't have an additive manufacturing machine to play with at this point. One thing I'd like to point out too is, like you say, we're brand new at this, and how do we increase our knowledge quickly? It was through the team, collaborating with the team, but also we were able to send David down to Lockheed Missiles and Fire Control in Orlando on a rotation, where he was able to spend time with Steve Rocco and company because of our network with Rare Parts team, and he spent a couple months down there learning the best practices on how to do this kind of work with all the various AM systems. And while he was gone, we were putting our capital improvement program budget to work, and when he got back, we had new systems installed. Next slide kind of shows our current state of the art here at Fleet Readiness Center Southwest. So as you can see, we have now an SLS, FDM, and SLA systems up there on the upper right. The support equipment goes along with them on the left, and then a myriad of tools that we've been working on with those tools, with that equipment since that time. And again, we're using this primarily for tooling, indirect parts, not really end-use parts, but we are finding applications where maybe we control the part and we can actually design something in additive manufacturing in mind, and come up with a really cost-effective, quick solution. So on the right side there, the lower right, you'll see that's a X47B hook point. And we got the 3D model. There were some issues with that part after the OEM. They couldn't engage the hooks at Pax River, so they had to redesign the hook hook point, and they had to get them made quickly. We had this attractive manufacturing capability in droves here, but we were able to take a design, model it in 3D, print it quickly in our SLA tool, and then send that part back to Pax River for fit check on the aircraft. And as we were getting that fit check, we had produced two of these at the same time, so we're using this other model to program our CMM machine while we're cutting chips on the actual metal part. So we sped up the production of that by a factor of 4 or 5 weeks by putting it all together and making this happen. So that's another real valuable tool that we're finding in the depot environment, is having the ability to rapid prototype and do a lot of the parallel processing. I'll go into a little more detail on some of these other parts as we get into the presentation a bit more. Next slide, please. As you know, we're still producing aircraft with certified approaches, and that is your subtractive manufacturing with our CNC manufacturing technologies. But we're working off of old 2D blueprints. The older F-18s, the E-2C, and most of the helicopters that the Navy or Marine Corps are flying today are still blueprint derived. And so, in order to manufacture repair parts or pieces of that aircraft, we need to convert those blueprints into validated 3D models. And so we developed a process by which we do that using not only drawing reconstruction from a 3D model, but using some of the advanced measurement tools we talked about earlier. And then now we're finding we can use the 3D printed parts there in that little circle you see, where we take the validated 3D model, produce the as a manufactured part for fit check and to accelerate our numerical control programming, CMM programming, while we're cutting metal, produce the part, and then we come back and measure that, verify it against the model to know we have a good part. And the approach there is kind of taken on the right side. You can see some of the software tools and hardware tools we're using to do that. That's sped up our manufacturing tremendously and given us much more accurate results and less scrap. So this process, we're trying to work with DLA to make this kind of the model and for acquisition of new spare parts. Next slide, please. I alluded to that we're using rapid prototyping and testing. So a lot of testing happens here at the depots, and we're finding that we can create custom grips, custom tools to accelerate our testing and give us good results. This is just one area where by expanding the awareness of not only our various competencies and our engineering teams, this capability, they come to us with all sorts of great new ideas. Hey, David, can you do this for us? And David puts his mind to it and comes up with some great ideas. And here's some examples of some of the stuff that we've done here just recently. We're involved in a lot of the engineering change proposals for these old aircraft, and in some cases do the design work ourselves and then create the kits. And so up on the right side, you see something that was done for the E-2C Hawkeye. It was a custom prototype panel that was created for a fit check in order to assess the design prior to going into manufacture. So things like this is where we find a lot of space and opportunity to use our equipment. Next slide, please. These are submitted by Yogi Kessler at Cherry Point. They're doing a lot of work with rare parts to get these products developed and ideas, but as their systems are starting to arrive at FRC East. But these are basically trim tools and drill templates that make a depot artisan's life a lot easier. We can get this stuff done quickly. So you see we have the ability to do scribe tools, offset tools, and drill templates for precision location of cutting and or drilling. And we use primarily the FDM, fused deposition modeling systems for this. It's really good at creating complex shapes. They're lightweight, and certainly they're more stable than some of the systems we were using prior to that with fiberglass and things of that sort. Next slide, please. Leads into production of end-use parts with FDM. And these are some of the sheet metal tooling. You saw an example on my earlier slide, but this is a great example that's taking place out at Cherry Point, where they're producing a very long part, upwards of 89 inches from FDM. And this is for both our hydroforming and our rubber pad forming. And we've been able to demonstrate both male and female shapes for blowdown tools, creating pressure intensifiers and or matched male and female tools, as well as some backfill tools to minimize the amount of time we spend with the FDM. And a range of thicknesses we've been able to test out here. as well as pressures. So this has really been a big cost saver for us, as well as speeding up our turnaround times on parts. Next slide. Next slide, please. Okay, this shows one of the optimized sheet metal tools that was being used at Cherry Point, and one of the things they did was able to test the various FDM products, whether it be ABS, plastic, polycarbonate, or the Ultem. And what we're able to show there is the range of pressures these can undertake before failure. And so with the various range, certainly prices rise as you go up into the stronger materials, but we can optimize the cost of the product we choose based on the application that's needed. You can see there for that rubber pad design tool that it was basically about $200 in material and an 8-hour build time to get that tool into the factory. So much less than it would have been to do it the traditional method. Next slide, please. This is another example of a complex formed part that came off of a FDM tool. You see the two of them there. And according to the Cherry Point calculations, this tool was 80-90% cheaper than it would have been to create this through traditional methods. So this is where, let me say, we're finding a lot of use for these as we wait for our opportunity to move toward end-use parts. Next slide. Stretch form tooling is another example of how we can produce parts rapidly. This is an FDM part as well. That was, you can see the size listed there, about 10 by 13, multiple contours, and we're able to form this with aluminum 2024-0 condition and up to thicknesses of 1/10 of an inch. And we're able to run this same tool 10 times successfully. And so it's this new capability that gives the depots added value. Next slide, please. Kind of gets into where we were looking. Yes.
I'd like you to just touch on these surfacely if you could. We're running short of time. I want you to get to your crowning glory. Okay, very good. Well, rapid composite tooling is kind of the crowning glory, I guess, with the advent of composite aircraft. So here you see the complex process we had to take traditionally to repair parts or produce composite parts. With the digital thread I talked about and how we can take those CAD tools and the scanning capability, we can produce a really high-quality 3D model, which would allow us to produce a mold tool. So that was the idea here. Next slide goes into a little bit more of the detail of need on the F-18 Super Hornet. A composite hat stiffener is found damaged in a lot of cases due to heat damage. And this hat stiffener is about 4 feet long, has a contour. You can see the shape there on the lower image. The panel's good. The hat stiffener needs to be replaced. And so to go get a new hat stiffener, we can't get one today. We have to buy a whole door. The doors are upwards of $800,000. So it'd be much more effective if we could produce our own hats as needed and fasten them to the door. So we took this project on, and next slide shows kind of a sequence of slides showing how it was done. We laser scanned the door and a hat stiffener. We produced a CAD model, and we took the most complex geometry there where the hat had multiple contours and wanted to prove an approach to produce tooling. It must be able to stand 350 degrees in the autoclave and 100 psi. Next slide, please. So we worked with Stratasys as part of the rare parts team through Connie and company, and produced some hat stiffener layup tooling from our CAD model. These were printed out of PPSF, and then we were able to fill them and lay up on those tools directly. Next slide, please. This shows kind of the process of layup and debulking of the composite parts. After it goes through debulking, then it goes into the autoclave. Next slide. You're able to pull those parts out of the autoclave and separate them from the tool, and we got great quality parts, very complex, put them through NDI, no voids, no disbonds, no delams. So we kind of proved this process works for us. Tool was intact and could be reused again for that matter. The only concern we had was coefficient thermal expansion differences between the composite and the tool. And so for a very large part, like the 4-foot long curved part, we wanted to look at some other options. Next slide goes into that. We worked with a company, Nevada Composites, which has a
a trademarked tooling material which matches CTEs very well. And in this case, we used a female mold used from polycarbonate in order to lay up this we call it green sand, and created a sand tool. And the sand tool, created the exact geometry that we needed and worked very well to lay up the same part. And so we have two approaches now that we look to create composite tooling. And this is going to be the approach we take to repair these doors and other parts of similar shape and size. So that kind of wraps up, I guess, what Connie thought is our crowning glory. I'd like to just go to the last slide, which talks about some of the closing comments here. As you can see, just from this example, there are plenty of indirect use cases within DoD sustainment facilities. We don't necessarily need to get to those end-use parts, although that is desired. But by doing these indirect parts, it gives us increased exposure to this technology. It gives our workforce the ability to think of new, innovative ways to use these tools. It certainly allows us to collaborate across the competencies and the enterprise. And I think what it's really setting us up for is the ability to support these future systems that will have a lot of additive manufactured parts in them. So with that, if there's any questions, I'd be glad to answer them.
Okay. I'd like to remind everybody that we are asking that you submit your questions to additive@ncms.org. Scott is here collecting them, and we'll organize them, and we will pose those questions at the end of this session to all of the speakers. So make it known which speaker you're addressing, please. Continue to keep your phones on mute, and our next speaker is Kyle Morris with the Naval Undersea Warfare Center in Keyport, Washington. He's been with this team for more than 11 years. And I want to, if you haven't already picked up on this, but Chris was talking about the use of additive in the tooling sector. Well, Kyle is also doing additive in the tooling sector, but in a slightly different way, as you will see shortly. Now, tooling is something in additive that we term as indirect. In other words, the part that you made is made by an additive tool. It is not a direct part as a result of an additive process. So Kyle, take it from here, please.
Hi, this is Kyle Morris from NUWC Keyport. I'm here with Bryce Weber. As Connie mentioned, we work with the NCMS team for about 10 years. It's been a very helpful group. We've made all kinds of different parts and pieces with our different systems. We have 3 different systems. We have an SLS system, an FDM system, and this system we'll talk about now, our rapid cast process. With additive manufacturing, there's lots of different ways to make different tooling, different fixtures. One of the ways is this process where instead of printing a part, we're printing a sand casting mold. So our machine doesn't make plastics or metals like some machines. Our machine actually makes sand. So we create a sand casting mold in our CAD system. Then we can send that CAD geometry out for solidification analysis and see if the casting rigging is going to work well. Once we have a go-ahead, then we will print a sand casting mold and send it to a local foundry. And that top picture looks kind of funny. It looks like there's a bunch of gold bricks on top of the mold. They're actually bronze or brass bricks just to weigh down the mold to keep the mold halves from floating apart. And then that's the actual mold we used for that lower part. The lower part is a vacuum cone. There's a vacuum or a priming system used on submarines that primes the trim and drain pump, and this is one of those components. The problem with this part is the OEM is pretty slow to produce parts and pretty expensive, and so if a ship needs one of these parts, it can be a real problem because they'll come in, say they need the part, and it'll take a long time to get them. So we've been working on reverse engineering these parts and then creating the casting mold and then printing those molds and cast those parts. Next slide, please. This is a really good example of showing you what our system can do. That top portion is a mold, and you can kind of see all the veins in that mold. In a normal sand casting application, you'd have what's called cores, which would go in the mold and kind of make the space in that mold for all those vanes. And so this mold with a traditional process would be, a 20-piece mold. With our process, we can just print that mold, that center section of the mold, in one piece and make the mold now a 3-piece mold instead of a 20-piece mold. And so it's much simpler, much more robust, and also you get a lot better accuracy on the spacings with those vanes. So it works really well for this application. This is another part of the priming pump. This is actually the impeller portion of it. It's the center section. Next slide, please. Another application that we've used for our sand casting system is the lobe part. It's kind of the housing of that pump. So another similar story. Create the CAD model of the part, then add all the rigging features, do solidification analysis, and then cast the part. Next slide, please. Another part that we've done, it's a similar part to the last one. The last one is an older style where red brass is used. This is a newer style that's actually a copper nickel version. So it's used on some of the newer submarines. In that upper picture, you can kind of see the gold center portion. That's the actual part. And then all the gray is all the rigging, all the risers and sprues and runners that get the metal to the cavity, and then also provide molten metal so as the part cools and solidifies. It keeps feeding the part so that any shrinkage that occurs during the casting occurs in the rigging rather than in the part itself. This is a kind of an extreme case. In most situations when you're casting a part, you'll have maybe an equal amount of rigging and part mass to the mold. In this case, we have about 4 or 5 times the amount of mass in the rigging as we do in the actual part. Next slide, please. Now we'll start talking about some of our additive manufacturing, direct parts. This is a shop accessory or a tool that we've used, and it kind of highlights that there's so many different parts and pieces out there in the DoD that are non-critical. There's been some discussion about certifying parts, and certification is a very important part of the process if you want to use one of these parts for a critical application. But there's a lot of applications where it's a non-critical application, and we've made thousands of parts with our systems, made lots of parts that are used for fixturing, for tooling, and then we've also used or made a few end-use parts, tactical use parts that are non-critical. This is not an end-use part. It's a tool that we use in our shops. And when we're building up torpedoes, we have a cart that the torpedo sits on so the mechanic can move it around between stations as the torpedo gets built up. And the outside of the torpedo has a real kind of a strange shape. And so there's these saddles that adapt the strange shape of the outside of the torpedo to the cart itself. The old parts were aluminum castings, and the shop came to us and said, hey, we want to make more of these. And while we could have made castings using our cast system, in this case it made more sense just to print the part using our FDM system. So we reverse engineered the part, printed the parts, and actually weight tested them just to make sure there was no issues with holding the torpedo parts, and they worked really well. So we delivered a batch of these to our shop, and now we're talking about, there's a couple of other customers that have come to us and want to make more of these parts for their systems, their shops. So normally, even if we made the casting with our system, it would have taken us, several weeks to produce the casting. Whereas with the FDM system, we can model it up and print it out, virtually overnight. Next slide, please. Another application of using FDM to make a few end-use parts. This is a large connector housing that's used in a training system on a kind of a dry part of the system. If we want to machine one of these connector housings, it would take you a long time to machine this part. Normally these parts are actually molded, so it would take even longer to machine the mold, to mold or cast these parts. But what we did is we used our FDM system directly, printed the connector housing, and then we're working on building this one up right now actually. So it'll be used on the dry side of a torpedo tube for a training system. Next slide, please. Another application of using these technologies as kind of a fixture or tooling, we had a customer that came to us, and the Navy has this deep submersible vehicle they can use for rescuing sailors in submarines if for some reason a submarine goes down. Hopefully that never happens. But this system wants to be always available and always ready. Well, there was some damage to this system, and they needed to rework some of the studs that mount different things. And they wanted some sort of fixturing or tooling so they could make sure those studs were all in the right spot. So they came to us, and we printed some fairly large FDM fixtures so they could check the alignment on all these pieces and make sure they were correct. So another example of where you can produce something very quickly, check your work, and then move on to the next step. So these additive manufacturing processes work really, really well for all these different applications where you need fixturing, tooling, stuff that's non-critical, but then also some non-critical applications. Any questions?
All right. Please submit your questions to additive.ncms.org.
Additive@ncms.org.
Yeah. What did I say?
Dot.
Oh, excuse me. Correct.
You can let everybody know we have a few questions, but you're going to hold them to
Yes.
the end, correct?
Yes, we are collecting your questions now. They are coming in, and we will hold them until everyone is presented. So, again, keep your phones muted. Our next speaker is Ken Cooper with the NASA Marshall Space Flight Center. And Ken is the advanced manufacturing team lead there. He's been with our program for 18 years. He is representing the use of direct parts or the making of direct parts using additive. Ken, please take it away.
Thank you, Connie. Can everybody hear me fine there? Are you hearing me okay?
Yes,
Yep, we got you.
Okay. All right, good. Here we go. So, yeah, like Connie said, we've been with happily with the NCMS team for quite a while. And we've been in additive manufacturing since about 1990. And over the years, we've tested 30-plus different technologies for different reasons. But it's just been in the last 3 or 4 years that things are really getting interesting with direct metal technologies, specifically the laser melting techniques. These are powder bed fusion, and some people call it DMLS, direct metal laser sintering. Some people call it SLM, selective laser melting. But it's that class of technologies I'm going to talk about, a few case studies today, and some of the cost and schedule savings we're seeing. To allude back to Andrew's talk earlier, our primary purpose at the end of the day is not to make the final hardware for flight. We're wanting to develop the certification and the qualification processes required so that we can shop out to different 3D vendors around the country to get our parts made cheaply and quickly, but know that they're making good parts. But yeah, let me go through a few case studies. If you go to the next slide, please. So early on, this was an injector faceplate assembly that we actually had made at one of the 3D printing vendors in Texas. And we didn't actually have our laser melting technique running at the time yet. So we shopped out a piece of this injector plate assembly. It was typically brazed together from various small little tubes, as you can see around the center lower images there, and it had holes as small as 62 thousandths of an inch, and we were able to combine a few small pieces into one assembly there and print that out, have the vendor print it out, and actually hot fire tested it over on the right there. That led into the next slide, if you'll advance please. We said, hey, if we can make the end piece of this injector assembly, can we build the whole assembly itself? And by this point, we had our latest machine installed on site. So we were able to print in the lower left corner. You can see where we printed the entire injector assembly. This is a 1,200 pound thrust injector assembly. Next to the lower left, kind of lower center there, you'll see a CT scan of this part. And that's where you can see where this technology really shines. See all those internal cavities and passageways? The coaxial injector, which means it's moving LOX and methane, and then mixing those out the tail end of it, and produces a really cool fire, as you can see over on the right side there. But this one had some really fine features. We were getting down around the 12 and 10 thousandth diameter holes through this. And we were able to combine that in and see some significant cost savings. You know, it was about half the cost of what it would be to make all these pieces individually and braze those together. And in a few months, about 21 weeks on schedule. Next slide, please. This is a main combustion chamber. We also pushing the limits of this technology, and something you wouldn't want to do any other way. If you look at the part in the center of the screen, the silver part with the quarter leaned against it there are actually conformal cooling channels, and they're actually flat in shape, and they go in just beside the quarter there, and they work their way all the way up the contour of that part, and then they do another dog leg back out, and so it's a really complex internal shape on those. Again, we could have made this by building the internal liners, machining out the grooves, and then depositing on an outer shell, but by 3D printing it, we were able to get these 30,000 diameter slots in there, and shave a good 11 or 12 weeks off our schedule and about 30% on the cost. And we were able to test fire that one as well with good results. On our next slide, this is a nozzle assembly, and this is kind of talks about the benefit of having your own technology in-house is the quick turnaround. The folks literally came over. They had some free time on the test stand that they could use if we could get them the part really fast. So we printed out, this is about a 6-inch diameter piece, and they took it real quickly. It only took us a day or two to print that, and they machined it down as thin as they possibly could. We printed it at 60 thousandths walls, and they machined it all the way down to 30, and then did some hot fire tests on those, and they were actually testing a new technology here at Marshall for advanced infrared technology for watching the hot fires, as you can see in the lower center screen. But we just were able to provide them a rapid turnaround, save them about 3 weeks. And actually, they probably would have missed their test schedule if they hadn't had that. On the next slide, the J2X gas generator, this was actually a couple of years ago, and this was the part that probably kicked off our renewed push in qualifying direct metal additive manufacturing techniques for flight. We did have this one built at a vendor, Technologies at the time, and as you can see on the far left center screen, you might notice the weld joints. This was a thick Inconel tube, if you will, that had a complete 180-degree radius, and it basically had to be built in stovepipe sections and welded together. But the project let us do a 3D print in parallel with the traditional technique. And we could get it almost 3 months quicker. We started later, so they came in close to the same time. Since then, luckily, we've actually found a vendor that can bend the pipes, the Inconel pipes, to the shape we need without it distorting too much. So we can get them made even quicker, or cheaper now. But at the time, that was a good cost savings of about 15%, and primarily on schedule. And it really kicked us off in buying techniques in-house and start this qualification process that we're doing now. If you go on to the next slide. Now this one, you may notice it's just a 100-pound injector, but on the schedule and cost savings, I couldn't put a number on it, because if you'll look at the center lower picture there at the cross section of this part, There's no other way to make this part. So there's really no way to compare the price and cost. We have, angled 10,000th inch diameter holes going through this thing, 37 of those guys around the center port. The designers designed it for 3D printing. They designed it for additive manufacturing. And we were able to crank this thing out in a couple of days. It was actually the first part we built on our selective laser melting machine a year ago, September. And they were able to put it through their flow test. They wanted to see if they could create this groovy little swirl injector, and it worked out great for their technique. We actually ended up making a few more before they started going out to 3D printing vendors and having these made around the country. Let's move on to the next slide. Now this one was a big one. This one was printed actually out at a vendor site. But this is a 20,000 pound thrust injector that's now been hot fired. Consisted of more than 100 parts in traditional make. This one was printed in 2. So we printed had the whole cavity body printed, and then just the face plate was a rigid mesh that got brazed on there. But the cost savings on doing it this way versus the traditional way, and that we used to make these swirl injector assemblies, is incredible. It was almost 95% cost savings. It was a difficult part to 3D print. It's very large. It maxes out the build envelope, and the vendor had to make a couple of tries at it. But even still, several months worth of savings and schedule time, and the cost is incredible. And this thing was just recently test fired here at Marshall, and with good success. And it's this kind of case study that you love to talk about and put out there to the world. We've had some press releases and some video releases on it, and it's this kind of data that we're adding to our mechanical materials and qualification database. It's these empirical studies that I think is going to help everyone out across the country, across the government. If you want to proceed to the next slide. Now this one is where I like to curb your enthusiasm a little bit. Additive manufacturing is a strong technology. It's great for lots of applications, and this was no exception. But it is a very large part, so it actually took 2 weeks longer than it would have taken to machine the part. As you can see from the cross-section in our CT scan there in the center, it was a very simple shape. So this could have been turned from a billet a little bit faster. It still would have cost a little bit more because you would have been whittling away, 90% of the material for waste, whereas we only printed what we needed. You can see on the far left side of the screen, this is the part coming up out of our machine, and this was a maximum envelope build. So typically our machine only built a 245 millimeter part by the height is 265 millimeters. This part was 285 millimeters tall. So we had to actually run a much thinner build plate that the part was printed on to even fit it in the machine. This is the longest run we've ever run. It ran a month long. It was about 24 days, I believe, print time. And but overall, as you can see on the right side of the screen, we were able to hot fire this baby. It's a 5,000 pound thrust nozzle. Got the guys some great data. Although it took us a little longer than traditional to make it, we still met their test schedule, so that wasn't really a big issue. But I just do like to point out that there are limitations to the technology. Size is king in a lot of the techniques, except for Kyle's huge sand printing machine he talked about earlier. So let's go ahead to our last slide here.
Hey, excuse me, Ken. This is Debbie here at NCMS. Our DCO connection has crashed here. So what we have to do here at NCMS is reboot our system. But we're hoping that the folks that are online with us will just have to refresh their browser. So if everyone could pause for a moment until we reset our system here at NCMS, okay?
No problem. Stand by to stand by.
Stand by. Okay, NCMS, we rebooted, so we're back up. If folks that are on VTC or who have speaking capability, if you guys could reach out to us and let us know if you see the next slide labeled Rapid Fabrication Hardware Gallery. Ken, can you see it on your DCO?
Yes, I have it.
All right.
We can see it here at North Island.
Here.
All right, got it. Okay. Go ahead, Ken. We're good.
Yeah, I was just wrapping up, actually. It was good timing. You know, cumulative, just in the past couple of years, I mean, we've seen, you know, 84 weeks cumulative schedule savings just in these case studies alone. We average 35% average cost savings. And, again, at the end of the day, we are just, we want to qualify the technology. We want to qualify the process. We want to put mechanical test data out on the street for these different techniques. We want to put some design guidelines out there for how we design for additive manufacturing. And then we also have a guidelines plan on, you know, how you determine what kind of test parts you want to build with each of your components. And we want to make people comfortable with putting these parts into you know, high stress, high cost applications, even human-rated systems. So, yeah, with that, Connie, I will turn it back over to you.
Thank you.
And you're on my screen. So.
Excellent. Thank you, Ken. I'm going to introduce our last speaker, Brian Anderson with the Anniston Army Depot. Anniston has been involved with NCMS in an additive relationship with us and the DoD for 13 years. And he is going to address the repair aspect of being able to use additives. So, Brian, are you there with us? All right.
I'm here.
Go ahead, take it.
You see the first slide there, this is typical representation of the things we deal with. Lots of components. This is a suspension arm for Abrams. I'm not going to go into the details of the repair, but most of these components are 4000 series alloys that are forged, heat treated, difficult to repair with other methods. Some repairs are done with some chemical processes which have other problems. But this repair was actually done by RDEC for us, and it's not approved, but it's out there, and I think TARDEC is also working on a repair similar to this, looking at the process parameters, material qualification, test requirements, those sorts of things that we don't have the people here at the depot to spend a lot of time on. If you look at a lot of these components, that if you're down at the depot, there's thousands of components around. These components will have hundreds or thousands of features. Usually only a couple of features that are worn render these components scrap. So there's a lot of opportunity for repair with additive. This actual part in this image is Abrams comp idler arm, which is up at the front of the hull. It's a one-piece forging. And it actually at one point in time shut the repair process down because of some problem with some of the contracts, and the supply system dried up. So logistics is important in addition to cost savings on these repairs. If you know, a lot of the vehicles within the Army are pretty old, and some of the vendors have dried up or moved on to other things. Okay, if you can look at the next, turn to the next slide, please. Again, this is another very similar example, a small shaft using a transmission. There's a diameter down at the bottom that's corroded, and adjacent to it, a seal wears a groove. There's some chemical repairs, plating processes done on this part. But in certain cases like this, you can actually enhance the part with additive using different materials that may improve wear resistance or even corrosion resistance. So you can make somewhat of a composite part with different alloys. You can get the strengths of the 4000 series alloys with some of the corrosion resistance of stainless or wear resistance also. Okay, if you can go to the next slide. This last slide depicts some of our early use with turbine, the AGT 1500 engine, replacement of balanced material, some blade edge and air seal type repairs. We had good results with this process, and I think this is some of the stuff done in commercial aircraft now. This process, you see the little note that says it's currently suspended. You know, Abrams and the TACOM went through somewhat of an evolution with the turbine. The original OEM, Lycoming, decided that they sort of backed away from producing this engine, and through a couple of projects, it ended up being now there's a new OEM for the old engine. So there was not a lot of data about the repairs. We didn't keep records such as was done in the aircraft industry, how many times parts were repaired. So it was agreed that when the new OEM started producing parts that they would suspend these repair procedures to sort of flush out and get the new parts into the system. Okay, if you turn to the last slide. This kind of summarizes our position. Additive's been around a while. It's shown that it has a value-added use there in repair. It seems to not be used as have limited use, and the only thing I can attribute that to is some of the administrative structure, I suppose, as far as collaboration, you know, optimizing material process and process specifications. I know TARDAC pushed through a spec recently, a DOD spec. There's an F-42 committee working on a spec. But when we go forth with a repair procedure, it goes through somewhat of a convoluted structure, and there's a lot of people involved that are not manufacturing savvy or they're not technical people. So there's a lot of difficulty in convincing them of this technology that they may never have heard of is a viable thing, and it needs to be adopted. So I guess one of the main focuses on our behalf is the structure, and it seems like that you know, I like the chart that I think it was Kyle had, or maybe it was Chris had, of the structure they had for advancing the technology. So that's all I've got.